Welcome to this mini lecture about data collection and preparation. Machine learning relies heavily on data, but raw data is often not ready for machine learning applications and must be processed. The quality of data is key to a model's performance. If you remember from a previous lecture, we described common steps in the machine learning process. After defining the problem, our first step is collecting and preparing the data in a form that can be used in modeling. After that, we will train the models, evaluate with different models, and improve as needed in order to select the final model for deployment. In this lecture, we will focus on the data collection and preparation step. Data collection is where everything begins. Remember that data are examples or cases from a given domain that characterize the problem we want to solve. Data collection often happens in parallel to the problem definition, and it is later formalized once the problem statement is defined and the project gets underway. Understanding the data for the problem to solve is very important, and I want to kind of stress this importance by describing one notable example from healthcare in the 1990s, which involved a study designed to predict probability of death for pneumonia patients. The goal was to identify high-risk patients who needed hospital admissions while allowing low-risk patients to be treated as outpatients. The trained model produced a counterintuitive result. It suggested that pneumonia patients with a history of asthma had a lower risk of death than the general population. This misleading conclusion stemmed from the way asthma patients were treated. In reality, individuals with asthma who developed pneumonia were typically admitted immediately in the intensive care unit and received the proper care. This proactive treatment significantly improved their survival rate compared to the general population. But because the dataset reflected better than average outcomes for asthmatic patients, the model mistakenly learned that asthma itself was a protective factor. Had this issue been identified and corrected in the dataset, the predictions would have been more accurate. So here we see the critical role of data quality in machine learning. The researchers wanted to predict what would happen from information available prior to admission, but they used data that contain information about what happens subsequent to admission. So there's a big problem with the data collected. Data can be present in different formats, shapes, and sizes, and exists in systems such as legacy machines, web, databases, flat files, sensors, mobile devices, and so on. Thus, the raw input data could be in unstructured format, such as images, videos, or text. They could be structured or tabular data, where fields are very well defined, such as spreadsheets, data tables, database tables, comma-separated value files, or tab-separated values files, or semi-structured data such as markup language, which contain tags and other elements that provide certain level of organization, but they really do not conform to a strict data model. Such examples are XML, JSON, and HTML. Now we're going to review some of these formats that we are going to encounter in the tutorials. Comma-separated value is one of the oldest formats still used and preferred by different systems across domains. It is one of the most widely available formats of data. In this format, each of data attributes, we have an example here, each of the data attributes is separated by a comma. The comma is a delimiter. This is an example taken from the COVID-19 complete blood count database. There may include also an optional header, like here we will indicate what each of the attributes are. In this case, we have admission date, we have age, gender, and so on. Optionally, enclose each of the attributes in single or double quotes. This is especially true when there is a comma in the data itself. Like in the highlighted example here, we have the treatment, which will be antibiotics and oxygen, and it's separated by a comma. So in order to distinguish from a delimiter, we use the double quote. Changing the tab delimiter from a comma to a tab creates a tab separated value file. This format is human readable, is simple, lightweight, easy to load. Kind of the cons is that there is no hierarchy and lacks data validation. Another example of structured data is structured data in databases like relational tables that connects data. And one such example is SQL databases and the way that is used in relational databases. And the way to access is either via SQL queries or interacting with database via the object relational mapper method. This is less human readable than the comma separated value format, but you can connect to powerful libraries or tools that are Python based, like SQL Alchemy, and the advantage over the comma separated value file is that it supports complex query. However, this system requires a database management. The box on the bottom right shows an example of an SQL query to retrieve specific gene expression data. That is, genes that have significant expression based on a specific expression threshold. To retrieve this, it will look into a gene and the expression tables. Markup language like XML defines rules for encoding data documents to be shared across the internet. XML is a format that is human readable. Its design goals involve strong support for various human languages and is platform independent and is simple. XML was designed to carry data with focus on what the data is. It contains some tags, as you can see, and these tags are custom-made. Another example of semi-structured data is Hypertext Markup Language, or HTML. It still is a markup language similar to XML, however, the focus is on how data looks, and it is mainly used by web browsers and similar applications to render web pages for consumption. For example, browsers use markup tags to understand special instructions like tab formatting, positioning, hyperlinks, and so on, but only renders the content to the end user to see. Here we have on the left, we have what is the HTML code, and then on the right, we have the corresponding layout of the web page for such code. And each of the tags indicates some styling or formatting defined by HTML. Another semi-structured data format that is widely used is JavaScript Object Notation, or JSON. And this is a lightweight data exchange format. It's a text format for storing and transporting data. It's self-describing and easy to understand. It's human readable. If we compare, it's more human readable than the XML and HTML. It's easy to parse in most programming and scripting languages. It's built on two structures, a collection of value key pairs and an ordered list of values. One issue with JSON format is that there is no enforced schema and can become inefficient for large data sets. Now that we went over the formats that are widely used for collecting the data, and we understand what is the importance of collecting a good data set, we're going to focus on data preparation. Data preparation is a process of transforming the raw data into a clean structure and meaningful format suitable to train and evaluate a machine learning model. The goal is to discover how to best expose the underlying structure of the data to the learning algorithm. Most algorithms are well understood and well parameterized, and there are standard definition and implementations. Each machine learning project, not algorithm, the project, is empirical rather than theoretical and requires systematic experimentation on the data. One thing that changes from projects to projects in machine learning is the specific data we used in that project. Thus, the data needs to be prepared so it can be consumed by algorithms. For example, machine learning algorithms expect numbers, and some algorithms cannot handle noisy data. And in all cases, the model performance depends on the quality of the data, as we just saw in the previous example use case. Data preparation involves several steps. Among these, we have data cleaning. A step is concerned with identifying the correct mistakes and errors in the data. For example, handling missing values, removing duplicates, correcting inconsistency. Then we have data transformation, where we have to do some encoding or change in scale or distribution of the input variables. We have feature selection, which is about identifying those input variables that are the most relevant. Feature engineering includes deriving new variables from available data, and dimensionality reduction is creating compact representations of the data. We're going to review some of these in the next slides or next lecture. In terms of data cleaning, the goal is to define and address specific observations that may be incorrect. This involves fixing systematic problems or error in missing data, involves deep domain expertise to correct specific data we need to understand in order to correct the data. And three basic categories of cleaning. One is basic, we just indicated, try to identify the systematic errors, do corrections, or identify redundancy. There's also, you can use some statistics to define normal data and identify outliers in the data that can bias the outcome of the model. And also identifying missing values in order to either mark them or impute them. Depending on the model to be used, data may need to undergo some transformation. By transformation, we mean a change of type or distribution of data variables. These operations are generally performed separately for each variable. The chart shows the different transformations that can be applied to the variables depending on the type of variables, either numerical or categorical. For example, for categorical variables, disregarding whether they are nominal or ordinal, we need to transform them into some form of numbers or vectors, and that is called encoding. We will review some of these in the next lecture. Feature selection are techniques for selecting a subset of input features that are most relevant to the target variable that is being predicted. Irrelevant and redundant input variables can distract or mislead learning algorithms, possibly resulting in lower predictive performance. So the goal of feature selection is to favor the simplest possible well-performing model by selecting the most relevant features that describes the data. Feature selections techniques are grouped into those that are applied to unsupervised or supervised methods. Within the supervised methods, there are three other further categories. Those models that are based on those models that automatically select the features as part of fitting the model, those are called intrinsic or empt models. Those that explicitly chose features that result in the best performing model, those are called wrapper methods. And those that score each input feature and allow a subset to be selected. Those are called filter methods. We will review some of these in an upcoming lecture. Feature engineer or engineering is the process of transforming raw data into features that better represents a pattern to the learning algorithms. Since feature creation depends heavily on specific data and datasets and data types, collaborations with the subject matter expert is often essential to identify meaningful transformations. This reliance on expertise makes it difficult to generalize feature engineering into a one-size-fits-all approach. However, there are some common techniques that can be applied across different datasets, and these here includes some of those. For example, just to name one, decomposing a compound variable, like extracting individual components from a field that describes date and time. The last method we are going to see is dimensionality reduction. And here, the curse of dimensionality is that the more dimensions the dataset has, the more likely it is that the dataset represents a very sparse and likely underrepresentative sampling space. The goal in dimensionality reduction is to create a projection of the data into a lower dimensional space that still preserves the most important properties of the original data. There are a few category of methods for dimensionality reduction, and we are going to review these in the next lecture. Here are the references that this lecture was derived or inspired on. Thank you.